Hi guys, Mr. Johnny here. In this video I will show you what the circuit is all about. That's a circuit I designed to replace one which is on my PCB drill press. I was not happy that this circuit has a large dropout voltage. It uses LM317 as a pass element, and it's a regular linear voltage regulator, has a quite high dropout voltage. So long story short, what that means that the motor won't receive all the voltage the power supply puts out. In this circuit, what it does is then, when there is no load on the motor is just freewheeling, the circuit will sense that the current through it is not large, and it will apply a little bit voltage to the motor, to the motor, so the motor spins slowly. And it is quite nice because it makes it a lot easier for you to aim with the drill bit into exactly right spot that you want, and also decreases the chance of snapping the bit in half or more pieces. But when you load up the motor by pushing the bit again into the board, the current consumption will increase, the circuit will sense that, and it will turn on this device as hard as it can. But again, this device, when it is turned on as hard as it can, drops a minimum of 1.8 volts. So the motor will get 10 minus 1.8 volts, which is kinda sad, because for using drill bits like 1.3 millimeters, I really could have used that extra oomph the power supply delivers. So I went and designed this circuit which does just that. Instead of LM317, this circuit uses N-channel MOSFET, and just like the circuit on there with LM317, when you want the motor to idle, it uses the MOSFET as a linear. In the linear region, effectively this little shebang with the MOSFET will act as a linear voltage regulator. But when the circuit senses that you want to turn it, that the motor is loaded, you want to apply the maximum voltage to it, the circuit will just go and turn this MOSFET voltage regulator into just a MOSFET switch. Thus you will get bugger all voltage drop across it, and it will be very nice. I tested it, it does indeed work better. So let me show you that it works. The port you see here controls sensitivity. Basically, sensitivity is the amount of current that the circuit will trigger on. You can set the sensitivity very high, and it will be enough to apply a light touch to the chuck of the drill in order for the circuit to apply full voltage to the motor. And if you set the sensitivity low, you will need to load up the chuck quite a lot in order for the circuit to send maximum voltage to it. Now, let me just show you that it works. When I'm gonna apply power, you see that the motor spins slowly, but if I'm gonna load it up, of course, it kinda misbehaves sometimes because it is on breadboard. As you can see, when I'm gonna wiggle some components, the motor will rev up and rev down and stuff like that. The breadboard is not really the best way there it is to construct these kind of things. The breadboard is not ideal for applications where you have reasonably high current, or some switching applications where you have high current and high frequency. The capacitance between the little rows of pins there, of holes there, is quite large, and for a high-speed circuitry it may cause a problem. Any road. I'm gonna now show you the schematic, and it looks like this. I cobbled the schematic together using the knowledge I already have. So you can see some standard building block kind types of circuits, like this amplifier using an op-amp, or this op-amp used as a comparator. And here is it, voltage regulator I talked about on the MOSFET. MOSFET is here on the low side because it's easy to drive it this way, and the motor is put on the high side, and I send the voltage across the motor with this transistor. So, for a start, let's say that's pretty boring, right? It's just a usual, your regular amplifier using op-amp, nothing to write stories about. Then the output of this is fed into this comparator, and when this value I sense, which is fed into the non-inverting input, gets higher than your preset, that's your sensitivity trim pot, the output goes high, turning on this transistor, and effectively when it does that, the circuit looks like this, like a MOSFET which is turned on through a 33K resistor. So, and as you can see, there are some components here. This little RC filter and this little capacitor is there to improve stability of the circuit, because the misbehavior you saw previously is because of the breadboard, loose contacts, and contact resistance, all that other jazz. I won't get into it. But the theoretical, not theoretical really, the real problem, instability problem with the circuit is the fact that it's a DC brushed motor, and there is a brushes and a commutator, and what that means, it spits out a lot of rubbish, and that rubbish in form of current spikes cause voltage spikes here, which then get amplified if this RC filter is not there, and then they are fed into this comparator, and if this capacitor is not there, a lot of them goes out, and now the voltage regulator superimposes those spikes on the voltage it puts out, and it's a closed loop full of rubbish, not good at all. That's why you see this RC filter there and this little capacitor. Now, yes, I'm using LED as a reference. The circuit is not a precision current source or anything like that. It doesn't have to be precise, plus it doubles as a power on indicator, which is nice. So, a little bit more about this voltage regulator. How does it work? Let's say you just applied power, so all transistors are off, and if this transistor is off, it's like an open circuit there, so there is no current through the motor, there is no voltage across the motor, because this point will be at the same voltage that this point is in reference to ground. 10 volts here, 10 volts here, 10 volts here in reference to ground. And if there is no zero voltage across the motor, because both points are at the same potential, the base of this transistor is at the same potential as its emitter, and this transistor is off. And when it is off, so will be this transistor. And you will have something like this again. So the MOSFET will start to slowly turn on. When it does that, there will be current flowing through the motor, which will create a voltage drop on that motor. And the voltage drop, and when the voltage drop across the motor will get high enough, eventually it will get to a point in 2.7 volts in my case with the values I've got here. This transistor will slightly turn on, and when it does that, it will source current into the base of this transistor, which in turn is gonna pull the gate to ground, turning this MOSFET off. That's how it maintains regulation. How to calculate the necessary values here? Well, this is nothing else than a resistor divider. You just use online calculators, or if you know that already, and you really should know that already, you can do it manually and use these parameters. The voltage here is going to be your input voltage of the divider, and the output voltage is going to be your base emitter voltage drop. But the thing is about this contraption is, oh boy, focus, not zoom, that the voltage across base emitter, you should not presume that it is 0.65 volts, because 0.65 volts is the voltage you apply to the base in order to turn the transistor on hard. Long story short, to saturate it. Here it is really used like a like a variable resistance. So you need just quite a lot lower voltage actually, 475 millivolts in my case. So it's not 0.475 instead of 0.65 volts. And that voltage is enough here across base emitter to turn this transistor on good enough for it to source enough current into the base of this one in order for the circuit to work. So use your desired voltage here across the motor, 2.7 volts in my case, and use the base emitter voltage here, and you'll get a result. I did some calculations here using the values I've got for 70 ohm here, 2.2k here. I did not use a trim pot on the breadboard to save space, but you can put a trim pot here, and that will be your idle speed control, and this is of course your sensitivity. So, how to calculate it? I'm gonna punch in those values, and you will see that transfer function of a divider looks like this. It is this value. It is the value of resistance of a resistor across which you sense your output voltage. Our output voltage is base emitter voltage here, so it's this resistor for 70 ohms. Here it is. Next you divide this value over the sum of these values. 2.2k and for 70 ohms, and here is 2.2k connected to the other side of the motor. Then if you do that, you'll get a value which is not 0.176. That's a transfer function of a divider. What this thing means is that the output of the divider right here across this resistor is gonna be a product of your input voltage by this value. So next you can I here did enough. Here I used another very simple formula which says that V motor is VBE over transfer function. VBE here 0.475 over transfer function which we calculated previously using these values that we've got, and we have 2.7 volts. Let me punch those in. As you can see, it's 0.475 over 0.176. If I do that, you'll see that the voltage should be 2.69 volts. Now let's test it. Does it match or not? And of course it does, because otherwise I wouldn't show you this. I'm not a free energy kind of fanatic. You can hear that the motor idles. That's off, no noise, and idles. So let's measure the voltage across it. 2.63. Close enough if you ask me, because the resistors I've used are 5% resistors. They have a tolerance, so of course it ain't gonna be bang on, but it doesn't matter here. Again, you can put a trim pot there, it will be perfectly fine. You will be able to fine tune the value what you want. Now let me show you a little demo where I drill some boards. And what better demo can you think of than drilling holes in the board that's gonna be used for this circuit. That's a board I laid out for it. Focus, you dummy. Alright, I laid it out today, and I made it today, and that's the main advantage of making boards at home. You don't have to wait, pretty much. You can make them in the same day. Yes, I know that you can order PCBs today quite cheaply and quite fast, but still, if I want just a simple board like this, do I really need to wait? Or simple board like this? It just works. Why not do it yourself? Plus it gives me an awesome feeling, because and that feeling is extremely pleasant if you have such scenario. You came up with an idea, you designed a circuit to make that idea true, something like that. You develop that circuit, you fail 500,000 times, but you still succeeded and the circuit is developed. Then you lay the board for it, then you make it. Yes, that's a bodge there because I forgot one resistor. And then you make it, and when you use it, you will have a very, very awesome feeling, because you will know that the board you're using, made by you, and the circuit you're using, made by you as well. It's a very, very nice feeling. Anyway, I'm babbling away here. Let me just show you some demo. Keep in mind though that the stuff is on a breadboard, so it won't really be a fair test. The fair test is gonna be when I'm gonna make this board, assemble it, then you will see all the circuit in all its glory. You will see why it is so good. Because on a breadboard you will have contact resistances and all that other jazz. It's just disgusting, really. Plus, all of a sudden, the circuit now desire to operate a little bit different. That is fine though. I have another circuit which I will show you. It is quite similar to this one, although it uses an entirely other principle. In order to make the motor run slowly, it uses PWM, and then it pretty much does the same stuff. Senses the current, and when the current is high enough, it just applies full voltage to the motor. But the advantage of that circuit is that you won't have the dissipation across the transistor you have now, because this circuit is a linear regulator on this MOSFET. And you will have a voltage drop across it, you will have current flowing through it, so you will have the dissipation on that device, which is equal to which is a product of voltage drop on that device times the current flowing through it. So anyway, who wants that? Let me give you some demo. I'm not sure if the thing will perform as good as it was once, because this video it's like a 20th attempt of me making this video, because I always get interrupted or something else. That's quite a thick board, as you can see, and it penetrates just fine. Now the circuit wants to misbehave. That's kind of... Before, it didn't do that. I don't know what happened here. Let me change one part. Okay, I replaced one capacitor, which you may see there. This one. There was a 100 microfarad installed, but now it operates as it should. It will, when I first apply power, it should rev up and then calm down. See? Now it will have full power, so now I can poke hole really fast. Just look at this. It has solder on it, so it stops the beat a little bit. Stops the beat a little bit. Anyway. I guess that's good enough demo, is it not? You see that the circuit drills very, very nicely. It doesn't drill like a million times better than the other controller, but it still it is still an improvement. I'm gonna quit it here before I make any more spelling mistakes and stuff like that. I showed you the circuit, I showed you that it works. Alright, thanks for watching, see ya.